Okay, here is Griffiths Quantum Mechanics Problem 2.9. This is, I think, either the last or the second to last of the infinite square well problems. I'm a little bit torn on which is more relevant, infinite square well or harmonic oscillator, but I'm excited because harmonic oscillator is next, and I do like harmonic oscillators. So just as a reminder, we're working with something that is going to be from 0 to A, where the potentials on each side are infinite, and inside there is zero potential. So we can have a particle is going to be trapped in the well. This is a very contrived situation, but it's still very useful. So this is building off of problem 2.8. So we had a initial wave function in problem 2.8 where at t equals 0, we had square root of 30 over square root a to the 5th. Sorry, that's not written well. So we have a to the 5th power to the square root, or you could say a to the 5 halves, however you want to do it. And x times a minus x. So that was how our particle looked at t equals 0. So it's kind of like we set a particle that looked like a parabola inside the well, and then we let it go. And over time, as time goes on to infinity, it is going to go to our regular infinite square well solution, where we're going to have, a sine and in pi x over a, so like some psi in for different energy states. So it is going to be artificially started as a parabola, and as time progresses, it's going to go into a sine function in order to fit those boundary conditions and be a solution to the Schrödinger equation. So for this one, we want to evaluate these. So these Cn, forgive me if I forgot exactly what page these are on in Griffiths, but it is in chapter 2. So these are our normalization constants, and we get those by integrating over x. Our sine wave, which is our general solution to the Schrödinger equation, and then times our initial condition psi. So this is going to give us multiple different values for each n. So we are going to have a different constant that's going to help us determine like the probability of, say, finding a particle in a particular energy state. And here's a bit of a spoiler alert. Ground state energy is gonna win. Okay, so let's go ahead and write this out, and I am checking my notes. Hopefully, sometimes I usually find I did something very sloppy in my notes, or I find a way to do it better. But since I'm doing these for fun, I don't really have too many apologies. I'm going to go ahead and multiply this through. So I'm going to have ax minus x squared. So we can pull out the constant there and also multiply through by ax and x squared. You will notice they have the same dimensions. A is in meters, x is in meters, or units of distance. If for some weird reason you want to solve it in inches, go ahead. The point is they're both distances squared, which is good. I mean, we want to have the same units. Certainly. Okay, so then I have square root of 30 times square root of 2, so I'm going to write that as square root of 60. Then I have square root of a to the 6, so I'm just going to go ahead and write that as a to the third. Now that's going to be multiplied by, we have our first integral is going to be from 0 to a dx, and that's going to be ax, so I could have wrote the a on the outside, sine n pi over ax, and then that's going to be minus the integral from 0 to a integrated over x squared sine pi over ax. Now when I was first doing this, I just kept making like a sign mistake. And I would even like plug it into Wolfram Alpha, and I was still making the same stupid sign error. The way to get around that, if you find this happening to you, is, despite what everybody says with like, common sense is not applicable to quantum mechanics, it totally is. Like, if you have distance, you still need units of distance, right? Like, it's not freaking magic here. It's just probabilistic physics. So I kept getting 0, and I was like, I know it's not 0. It's like, I know better than that. So I'm going to go ahead and do a U substitution on this guy because I learned math the Russian way. So we do U substitution. Okay. I like to go ahead and change the limits. I know not everybody does, but I'm very prone to just making dumb mistakes, so I prefer to just, write everything out, and then I can check it as I go. Like, I don't have any math balls, so I don't get like self-conscious, I guess, if I'm writing out every step. Now, admittedly, I kind of used to, like, I never would have ever done math in public when I was a student, because, like, I just thought I was so dumb, mostly because my classmates would tell me I'm dumb. So I would be horrified at trying to do something, certainly on the board, would just be a nightmare situation. And then I just kind of, I got older and I learned to just get over it and, accept the fact that I can't do everything in my head. I never could. And that's okay. I'm going to just do it my way. And I'm happy with that. So that's my little world advice, life lessons for anyone who might be a math student now, because, people are mean, and I know you might be hearing some mean things, so I wish I could tell you it gets better. It really doesn't. But you get to choose who you hang out with. Oh, whoops. I was putting in U's. See, that's what I get. So I'm just copying this from, like, an integral table, by the way. So I have 2 minus x squared times cosine x plus 2 sine x. Admittedly, if my integral table had included a constant in that second integral, I probably would not have done a U substitution. But as we established, I'm very literal. I like to write out every step. And I'm doing this for fun. So, like, how often do you get to do integrals anymore? Okay, so the first one, it's a little bit confusing. How about we just call that B, so that this can be a little bit more clear, that I'm not talking about the same A there. And then B is going to equal n pi over A. So what I get for my first integral is I have a, because it's times everything there. And then that's going to be times negative x over b. So that's going to be over n pi times a. And then that will be cosine of n pi over a x plus 1 over b squared. So that's a squared n squared pi squared. And then that's going to be sine of n pi over a. And this is all going to be evaluated from 0 to a. So a lot of you probably notice, yes, the sine terms are going to eventually go away. And I'm still writing them in there just because. Now that's our first integral. Now my next integral is going to be this u substitution guy. So I have out in front these constants. So I have a cubed, n cubed, pi cubed, multiplied by, now we're going to look at my solution. I have 2 minus u squared times cosine of u plus 2u sine u, and that's from 0 to n pi. Again, as you can see, with those limits, sine of 0 is 0, and then if I have sine of n pi x, it is going to go away. So if I evaluate at these limits, my sine term just goes away because it doesn't exist in either of those limits. My second sine term also is going to go away because it's also going to be sine of 0, which is 0, and sine of n pi, which is 0. There's our sine, and there's our pi's. Versus our cosines looking like this, where it's a 0. And then that's going to be pi halves, so we'll call that one pi, and then 2 pi. There we go. It's a friendly reminder to help me keep my signs correct, because I will tend to mess them up. Okay, next line, I go down. I have square root of 60 over a third. Now I have a. I'm going to evaluate this. I have at my final minus my initial. So my final is going to be x equals a. So I get negative a squared over n pi times cosine n pi. And at my initial minus my initial, a cosine of 0 is just 1, but it has this guy here, so it's just 0. So that one all goes away. Then I have negative a to the third over pi to the third times n to the third. And then I have my limits. So I'm going to do n pi, my final. So I have 2 minus n squared pi squared times cosine of n pi. And here's where I kept making my stupid mistake. Then, which is, I mean, I like stupid mistakes because I can fix stupid mistakes. Minus my initial is going to be 2 minus 0. But then I just have cosine of 1, or sorry, cosine of 0, which is 1. So it's just that. I kept writing like in pi again. It was very silly. Okay, so my first one, I get a negative a cubed, which makes me very happy because I have an a cubed in my second term, meaning that my dimensions are the same, so I'm happy about that. And then that's cosine in pi, and we could just multiply this guy through. So I get 2a3 in pi 3 pi plus, now I'm going to have a to the third, but you see my in pi squared and pi squared are gonna cancel out those guys there. This is looking very convenient, isn't it? And oh, whoops, I forgot to write that they're both times cosine in pi. That's another very important thing to make sure of, because that kind of makes our solution, right? Okay, and then that's going to be minus 2, so then we get minus times minus plus. Again, very convenient, isn't it? It's almost like somebody made up this problem for you to solve. And those guys are gonna go away. Oh wait, no, sorry, not those guys. Wrong ones. These guys are gonna go away. There we go. These guys almost go away. Not quite. Because I have a factor of cosine in pi, which can either be 1 or negative 1, depending on if n is odd or even. So, but what's nice is that I have this very convenient a to the third, which I can go ahead and factor that guy out, so my a to the thirds cancel out here. Then I still have my n to the third pi to the third, and then what I have, oh, and I can just let's get that 2 out of there too. Then I just have a 1, and then it is minus cosine of n times pi. Yay. So this is a really fun little result. Because what it told us is that we have a difference between our odd states and even states. Because if n is even, then cosine is negative 1. So then we get 1 minus negative 1 and 1 minus negative 1. So 1 plus 1, we get 2. Or we could have our n is oh, hold on, I wrote that wrong. It was like other way around. See, this is why I draw stuff. I'm gonna draw it better because I can never remember. There we go. There's pi. There's 2 pi. Better drawings help. So backwards from the way I said it, if we have n is odd, we get 1 minus negative 1 is 2. If we have n equals something positive, we have a 1, so we get 1 minus 1. So only the odd states are present, which is kind of fun. That's really cute result, actually. Then I think I wrote these down in my notes. Typically, I don't do numerical results because I'm not really too into numerical solutions. I usually only stick with analytical. Certainly people who are better than me can do more complex numerical solutions, but this is pretty simple. So we just have C1, C2, C3, and I don't even have to do C2 because it's 0. Alright, so I'll just write them out. I just put them in a calculator. What else am I going to do? So I get 2. Oh, I did work this out. 60 is 2 times 30. 30 is 2 times 15. So I get 2 times square root of 15 times 2. So 4 times square root of 15. And then we have 1 to the third, which is 1 over pi to the third. And then that's times 1 minus 1. And what we can see is it's that ground state energy, right? Has very high probability. And then if I do C3, we get 4 times 15. And you could tell it's going to be smaller because, well, it's going to have this factor of 2 to the third that it's divided by. So, basically what we have here is we have a series where, what it boils down to is 1 over n cubed. So you're going to have 1 over 1 cubed plus, and then I should say k, because then they're only the even numbers. So 1 over 2 cubed, and then 1 over 4 cubed, etc. Clearly, that is going to be a converging series. This is not going to blow up to infinity. We get a massive amount of decrease with each term. And then you add them all up. The result we're looking for is the sum of all of these constants should be 1. So if I took this sum all the way out to infinity, I have a 100% probability of finding my particle in a state between 1 and infinity. As you can see here, highly most probable state is ground state. Now when I add up mine, I do get a little bit, I got a little bit more than 1. I'm going to attribute that to sloppiness on my account. I can't remember what I got. Oh, there it is. I got like this. So that seems a little bit too much higher than 1 than it really should be. So I'm going to assume I probably missed some sort of numerical factor in there somewhere. Or it's just that much of an estimation. So the next part of the question, it asks, it's kind of fun, knowing that immediate repetition of the measurement must return the same value, what can you say about the coefficients after the measurement? So basically, I have my particle in the well, and I go to measure its energy. I have a very high probability of getting ground state energy. But once I have measured it, if I immediately after measure it again, then it must return the same value. We're talking super ideal conditions immediately after. So that means that this factor here is not representative of what you would get or what your probability is after you have collapsed the wave function, which makes sense because once I calculated this guy based on this wave function, right? This is how I got those numbers, was using this wave function. Once I have collapsed the wave function, the wave function is no longer representing my particle, so this is no longer really representing my probability, which is kind of fun, I think. So that's kind of, I mean, for me, that's very brief solution. And basically, once you have measured it, you have collapsed it into that form, and now you have a different form. You've collapsed it. It no longer exists in the initial condition that I defined before because I collapsed it. So this is a fun little result. Not such a bad problem, as long as you use your common sense to test it out.